Hello, today we are talking about what's called Euler's method. It is spelled E-U-L-E-R, however, it is pronounced Eulers. So this is a method to actually find an approximation to a particular solution with a differential equation. So looking at what we've been given, we have dy dx is 0.3y. So number one says, well, just write an equation for the differential dy. dy simply means isolate dy. So all I'm going to actually do is multiply both sides by the dx so that dy is by itself. And this is what I end up with. Number two says find dy at the point 1, 2, so x is 1, y is 2, if dx, the change in x, is 0.5. So then dy is going to be equal to 0.3. I'm going to plug in 2 for y, and I'm going to plug in 0.5 for dx. And then I'm just simply going to use my calculator and evaluate that. If you don't have your calculator, I apologize. Pause the video and go get it because you will need it throughout this exploration. So when I evaluate that, I get 0.3. So dy is 0.3 and dx is 0.5. In number 3, it says, okay, add this value of dy to 2. Well, where did this 2 come from? Well, initially we were given that we were starting at the point 1, 2. That means when x was 1, y was 2. We also know that we had our dx was 0.5, which means our next x value would be add 0.5 to 1. That would give me 1.5. My new y value would then be take the 2 and add dy to it, which would give me 2.3. So y is approximately 2.3 and dx is 0.5, and that was when dy was 0.3. So all we did was use the differential starting at the point 1, 2, knowing that our change in x was going to be 0.5 to figure out an estimate for the y value at x is 1.5. So number 4 says, okay, estimate the value of y at x is 2 by finding the dy at our new point. So what we're going to do now is we know what dy is, and dy is 0.3 y times dx. Well, we have a new y this time. So my dy is going to be 0.3 times my new y, which I just found, is 2.3. Oops, I'm writing 2.5. Times my dx, and my dx is still 0.5 because I've gone up 0.5. So my dy in this case, using my calculator, is 0.345, which means I need to estimate now what the new y value would be. So that tells me that my y value is going to be the 2.3 that it was plus my dy, which is now 0.345. So the y value is 2.3 plus 0.345, which is 2.645. So what that means is, when following with my chart up above, kind of bringing it down, when x is 2, my y approximation is 2.645. So what Euler's method is doing is it's giving you, we have a starting point, which in our case was 1, 2. We have a change in x that we're going to use, and by using our differential dy, it's telling us what our new change in y is every single time, and it's giving us a new estimate for the next y value based on our dx. So if we look at number 5, all the answers that we have found so far are right here in the table. We started here where x is 1 and y is 2. When we evaluated our dy, I'm going to go ahead and write dy right here so I can see it. And it was 0.3 times y times dx, I believe. Using our differential, we found that the dy was 0.3. Then we moved on 2x is 1.5. Since we knew this 2.3 comes from adding those two things together. So 2 plus 0.3, that's giving me my 2.3, the next y value. So when I find my 2.3, then when I'm finding this 2.645, I add these two guys together. That gives me 2.645. And again, I find my dy the same way every time. Now I'm going to use my calculator and the store button to show you how I would do the next one. So with your calculator, I'm going to find my dy, which is 0.3 times the y value right now, which is 2.645. And then I'm going to multiply that by dx, which is 0.5. So I calculate what that is, and I get 0.39675, I believe. So write that down. Now we're getting to the point where these numbers are getting larger and larger decimal values, meaning more decimal values. So I'm going to go ahead and store this in, not going to store that, sorry. I am going to take that answer and I'm going to add it to my previous y value, which is 2.645. And I'm going to get my new y value. So my new y value is 3.04125. Once I've got my new y value, I'm going to store that in A. Then I'm going to calculate my new dy. So again, I'm going to take A times 0.3 times 0.5. This is my new dy, 0.456. So again, I'm going to write that dy down. So 0.4562625. And on my calculator, I'm going to take that, I'm going to add it to the y value, which is stored in A. You can store it in y if that makes you feel better. And that's my new y value, 3.498. I'm going to store that back in A, and I'm just going to use A for my y value every single time. So what I want you to do right now is I'm gonna write down all of the answers. So I want you to just keep working. Once all the answers are up on the screen, however, I want you to pause the video as you keep working to make sure you're getting each answer correct as you go. I don't want you to do the whole thing and then come to find out you had a mistake somewhere and you have to go back and redo the whole thing. So go ahead and keep working this out, and the answers are going to appear momentarily. So the answers are now up on your screen. So please pause the video now as you work through this problem. And when you're finished, press play again so that we can move on. Okay, so now we are on number 6. And I apologize, within number 3 I was supposed to plot some points and I hadn't because I want to talk about this graph in number 6. Number 6 is showing what's called a slope field. So what it's showing is the slope of a tangent line at each point that is a lattice point, meaning a corner on the grid. So not at like 1.18.3, it's at 1, 1, 1, 2, 1, 3, 4, 1, 4, 2, 4, 3, etc. So I needed to actually have plotted some points. So in number 3, it asked me to plot the point 1, 2 on the graph. So 1, 2 is my blue dot, and then 1.5 with the y value I had, which was 1.5, 2.3. So 1.5, 2.3 is about right there. And then we need to do number 6. So it's asking me to actually plot all of the y values from number 5 that we just found. So go ahead right now and just plot all of your points from number 6 onto this graph. So pause the video now, please. So here are my points plotted. And again, these are going to be approximations. And then it says connect the points with line segments and show dy and excuse me, show dx and dy for certain points. So if we go ahead and kind of eventually what we're going to do is not connect by line segments. We're going to connect by creating an actual curve. And I apologize, my alignment's not very good today. So here's a basic idea of what this curve would look like. And again, we're just sketching that in. And then they wanted to know what dx is at point 5.5 and 6. So the dx is my change in x, which is right there, and my dx should be 0.5. And then the other thing we were asked to find was dy, and my dy is right here. And you can tell if you look at the end, my dy is very large. When you look at the very beginning, if I kind of draw in the dy, my dy right here is very small. However, my dx is exactly the same. My dx is still 0.5. So the dy was not a constant thing going on throughout the whole time. So moving on to number 7. Number 7 says, okay, great. Now solve this differential equation algebraically, and then let's check to see how accurate our Eulers method is that we did for coming up with a actual solution at x is 5 versus what we get algebraically. So what I would like for you to do right now is start with dy dx is equal to 0.3y. I want you to solve that differential equation. And once you have that solved, go ahead and put the video back on to make sure you have the right solution. Then we'll work out what y is at x is 5 and check with Euler's method at x is 5. So go ahead and pause the video now, please. So this is what I got from my particular solution, and I didn't write the entire value of C out, but my C ended up being 1.4816. So please pause the video here if you're having a problem getting to that point. Otherwise, we're going to answer the questions. We want y at 5. So y at 5, I'm just going to plug in 5 for x, and when I did that, I got 6.640233845. And when I compared that to Euler's method, it was about 0.5 more than Euler's. So not too far off, not really that accurate. Euler's method is much more accurate the closer you are to the starting point. So if we were using an x value of 2, our answer using our differential equation would be much closer to the Euler's method answer. So that is Euler's method in a nutshell. You will have to be able to do this. In order to do Euler's method, you have to have a starting point. You have to have a differential equation. You also have to have a change in x. Those are the things that you will be given when doing an Euler's method problem. Well, thank you for watching. Have a nice evening.